This presentation is about heterogeneous compute. If you're in the wrong room, now's the time to take off. Heterogeneous compute is a really big deal for Qualcomm. We have a large set of different processors on our system on a chip, so you'll hear me use the phrase SoC several times, I'm sure, in the next 10 minutes. I'm just going to provide a sort of brief introduction to the deeper discussion that Purnam is going to follow up with. So without further ado, we want to kind of present heterogeneous computing to developers that are in this room as a way, as a new computing paradigm. We look at it as something that can basically really allow you to enhance the performance of your applications by basically making intelligent choices about where you run your applications, on which processor to take best advantage of it at the right time. We feel like you can have exciting applications that fall within essentially the power performance envelope of our mobile platforms that exist today in a way that's better than, for example, just brute force running everything on a single core like the ARM processor or our Crate processor. So that's sort of the main point for this one. We've got a large number of sort of dedicated processors on our SoC. We've got a Crate, which is our CPU, quad-core Crate on the 8974. We have a GPU, the Adreno class GPUs. We have DSPs that we refer to by their marketing name as a hexagon processor. So you may hear that phrase used interchangeably. And we have additional hardware on there, that people can leverage to do dedicated processing. For example, with the camera, we've got our integrated signal processor, or ISP. Actually, going forward, we actually have a dual ISP to handle very high resolutions input sensors, and so we're looking to be best in class in supporting high-res sensors for advanced cameras coming forward, and certainly the most advanced is Purnam's coming, so you'll be in a great position to talk about that later. The idea is that there are many different things being done on mobile platforms. All kinds of different applications are really being used. Everything from photography and video, which is something that's near and dear to my heart, but there's more sort of conventional tasks, like, for example, web surfing and data usage. Email is certainly something that sort of has an interesting user interface. You've got all kinds of computer vision features that we're bringing in. We're actually demonstrating a tracker that was out in the actual demo floor. If you haven't seen it, please stop by. The tracker is an interesting feature that we think is an example of a computer vision feature that can basically leverage the input camera sensor and then essentially allow you to pick regions of interest that make most sense for you, and maybe potentially couple that tracker to our 3A algorithm, which is autofocus, auto zoom, auto exposure, and basically provide a really nice camera feature for you. But basically the point is with this is that there are lots of different things people are doing on mobile, and not all of them have the same design constraints or requirements, and so you pick the processor that best serves your purpose, and we are happy to support a breadth of different processing types, and that's essentially heterogeneous compute. The design requirements vary from power to performance to longer battery life, all kinds of different constraints that really are present on mobile that are different than, for example, on a desktop or maybe larger form factor devices. And we feel that by providing the heterogeneous set of options to app developers, you're going to be well served. So, an example, just picking the first three, or the main three, if you will, our CPU, our DSP, and GPU, they have different characteristics that make sense to use in different areas. Our CPU basically is well served for things that require large amounts of sequential logic, and so essentially, if you have to make a fair amount of logic choices that the actual CPU is better handled to do in a very high performance manner, Our crate processors are well served. They're basically running now at over 2 gigahertz. So you get very high performance in terms of time to execute a particular task, and you get a fair amount of control over the algorithm that you're trying to run on the CPU. So that's a great choice for certain applications. Our DSP is an extremely low power, very high performance DSP that's actually really well suited to again, branching algorithms that actually require a certain amount of logic to be implemented and executed on the DSP, but also do it at a very lower power point so that maybe it could run longer, not burn as much battery life. And so in a lot of these always-on use cases, the DSP is a preferred choice. We'll show some examples there. But lastly, you've got the GPU, which is traditionally done for very parallel processing. It's very well suited to rendering and compositing, and so all kinds of traditional use cases make sense to do on the actual GPU. In addition, the GPU has OpenCL, which is a programming model that allows you to basically do general purpose computing on the GPU hardware. And so it's particularly effective at some of these image processing tasks. So, like we've discussed earlier, there's different sort of vectors in which you can sort of measure performance, and what is optimal for one developer will be different for another depending on the use case. So here we're showing 3 different scenarios where, depending on where you what you're doing, you may have like a video conversion task where, in terms of latency and energy, it's probably optimal to run on the CPU. For example, character recognition, for those of you familiar with optical character recognition, reading text through the camera interface, you end up being able to use an underlying algorithm called MSIR. It's a fairly heavy-duty algorithm that can sometimes be multi-threaded depending on which way you're actually implementing it. But the idea is that you end up sometimes you'll trade off a little longer time to execute and basically have a lower energy performance for something of this sort if it's on a fair amount of the time. So this is a good example of where the DSP is sometimes better suited to such an algorithm. And lastly, the GPU is fine for different kinds of denoising algorithms. When you whether you know it or not, when you use your camera to take a picture, there's a fair amount of denoising that goes on under the hood to kind of make sure that you get a high quality image. And our GPUs end up being the dedicated or the processor that does most of the denoising for us. So it does a particularly good job in that regard. So going forward, we've got this computational camera term that gets thrown out there. And computational camera, you can, for the purposes of my initial few slides, will refer to basically doing something on the camera with the images that you gather that's beyond the traditional take a snapshot or do motion video, which are the traditional use cases for camera. So we've got some examples of things you can do on our Snapdragon SoC when you have the additional benefits of the crate, the Adreno, and the Hexagon processors, as well as the image signal processing capabilities. And so, like I mentioned earlier, we have a dual ISP that allows you to basically handle one very large sensor or potentially a couple of input sensors. In this case, we're showing a dual camera configuration, and some of the benefits of that allow you to do interesting photographic effects like the Bouquet Effect, which is admittedly spelled B-O-K-H, but the Bouquet Effect is an interesting effect in portraiture, and that's not something you typically associate with a mobile platform. But it is something that you can now do when you have this additional hardware and processing capabilities. And so the lady in the foreground is in focus and is nicely illuminated, a very nice picture of her. And in the background, what you're doing is basically you actually have a slightly defocused and blurred, and it's actually a fair amount of effort going into the optics on the $1,500 lenses that a portrait studio might actually use to create this effect for your kid if you ever went in there, or your wife or significant other. And so in this case, those octagonal shaped light rays that are coming back are definitely by design, and they're kind of an artistic effect. There are ways to basically provide this using the tracker that we're providing, showing outside, which is a computationally intense algorithm. And again, you can kind of mimic that using the additional processing capabilities we're providing between our camera and between the actual back-end processing. And so, additionally, as part of in this suite of camera features that we think are exciting with our dual ISP hardware and the programmable additional processors, you can actually take a picture and essentially decide where you want the focus point to be. And we have a sufficiently high throughput image signal processing hardware that you can take in burst mode several pictures, and you can take them at different focus points, so you can adjust the actual focus value on the actual hardware. And by doing so, you can allow in sort of a camera application that might run on your mobile device, essentially a user selectable focusing of the images that you gathered. And so we've got examples in this case where you have a series of friends, and you're focusing on different people at different times. So depending on who you wish to show this photo to, you can focus on whoever you like. But it's a good example of being able to augment the experience of mobile users and provide features that were previously kind of reserved for maybe SLR type cameras or higher end photo editing that might be off on your computer, and you might not actually get around to that. And so doing it on the device, you actually enhance the experience for folks. This is a good example of depth mapping, and so it's an unusual looking graph, but bear with me. So with two cameras, you're actually able to basically kind of get a very crude estimate of depth in a picture and be able to kind of portray that in a histogram to an algorithm, which is what the Excel graph is showing here. It's this disparity histogram. And so by being able to kind of do this programmatically and get an estimate of where the depth is, one of the features for that, which is actually kind of cool, is instant autofocus. And so when you have a typical autofocus algorithm as we have today is a feedback loop that basically trains in and takes a few milliseconds to be able to find the focus point. Actually, you'll see this when you try and scan a business card using your phones today. And so the idea is that with multiple cameras, you'd be able to kind of at least have a faster focus time. And so that's very useful for a variety of applications, including the Vuforia augmented reality feature set. And so a lot of these complicated value-added software capabilities that come with Snapdragon will be only enhanced when you have this kind of additional processing power. And so many of you who were here last year were actually presented a FastCV presentation. And FastCV, for those of you who don't know, is our low-level library that basically is used to accelerate using hardware on our SoC computer vision applications. And we do that by basically hardware accelerating the implementation for these low-level building block functions within our FastCV library. So if you're running your app on a Snapdragon device, it runs very fast because it takes advantage of the DSP, the GPU, and our Venom is a Neon Cindy engine that basically is located with our crate, and it does very fast Cindy calculations. So in this case, what you end up having is FastCV being the underlying building block for higher level features. And so we're calling that group of high level features that we're looking to make available to partners Snapdragon Computer Vision Engine, just generically. But an example of that would be essentially the tracking algorithm that you see on the floor today. It's a tracker that we're looking to incorporate to couple with our 3A algorithm built into the camera, and do additional post-processing capabilities in some of the features where you can take a region of interest with the tracker and basically filter things independently. That's an example of an application that's built on top of the FastCV library. And so these are basically the beginnings for a new set of features that we're looking to bring to the market. And we sincerely would love your feedback, maybe now or after the presentation, anytime really. But basically, the idea is to show to developers that you can do an immense amount with the hardware we're providing, and we really look forward to basically your feedback and future work. So with that said, this is a really short introduction to what we're providing, and I'm going to hand it over now to Purnam from Pelican to give you a much deeper presentation on the Pelican camera.
Hi, so I'm Purnam Sheth. I'm the Vice President of Engineering at Pelican Imaging, and we are doing, I think, something very unique in imaging. And part of my talk today, we'll talk about how we're actually leveraging the Qualcom Snapdragon, I think in a unique way, but I think something that's going to become more and more prevalent as we go forward. So what do we do at Pelican? We actually do depth-enabled imaging. And when we're looking at building our product, right, we're looking at some key characteristics that our customers gave us great insight, but also where we think the future of imaging is moving. We all want is a small and thin form factor. So our particular form factor is half the thickness of a traditional camera. And for those of you in the cell phone business, know that the thickness of your cell phone now is dictated by your camera. That is the thickest part. So this allows a whole new set of industrial designs for cell phones. Depth-enabled imaging, I'll talk a bit more about that. We want to make sure that as we're looking at building this, that we have the processing performance, the power management, all the things that are important in a mobile device. As our particular technology is really targeted at mobile, although we're finding there are many other applications as well. The other thing that people always talk about is I want fast shot-to-shot. I don't want any delays in what I'm doing. But the key thing, and this is, that we're really trying to change, is it's not just about the picture you take. You want to take a good, great picture. But where will imaging go forward? When it's not just about the picture you took, but what you can do with it. So we have a number of features that we have with our camera. It's an array camera, right? We have 16 cameras. They're all independently controlled. And what we do is we actually take those images, fuse them together, create a depth map. And with that depth map, I actually have the distance to every single pixel in the image. What that lets me do now is a whole set of features. Everything from being able to focus or refocus the image at any point in the image, and even pick multiple points. So I can focus, for example, on the girl in the front and the San Francisco Golden Gate Bridge there, and I want to blur everyone else around it. As an example, I can do multiple of those as well. And this is something when people see it, we were demoing it at Hardware Day, it's kind of cool. It means that whenever I take a picture, I don't have to worry about something being out of focus. Because in our particular camera, we don't have an autofocus. We don't even have a shutter, right? So this is a very big difference in terms of getting the shot every time. So every picture we take is actually fully in focus, right? There's no area where it's in focus and the other area is, blurred. With depth, though, I can now start to do some pretty amazing things that you typically try to use Photoshop to try to emulate in a rudimentary way. For example, I can now select objects with very high accuracy, right? In some of our algorithms, when we're actually automatically carving out people or objects, it comes right down to the hair. We can actually do that by using the depth information along with luma, chroma, other pieces of information. And, be able to cut, paste, resize. The thing is, when you're looking at these pictures, think of it as a 3D picture. So when I take a person, I can push them into the picture and automatically scale them appropriately. So that there's really depth information with every particular piece or segment in this picture. And on the right there is just a part of our depth map, if you visualize it, for the I guess the ladies up above. So it lets us very accurately select and be able to do things with those objects. And so if you just look at that, that's just kind of the tip of the iceberg when you start thinking about object detection, recognition, and we'll talk about a number of other industries that this technology is very much applicable for. This actually is a video, but I'm going to tell you what, I'm just going to skip past this one. And what this was really, you can actually see the same thing on our website where we actually can, focus and refocus on multiple areas of the picture. So you really have, and I guess the other key thing I didn't mention, it's all on your mobile phone. This is not sending it to the cloud and doing something. It's not taking it to your PC. This is all on Qualcom mobile phone or tablet. Here's an example on our depth map where we have our input image. This is our intern, Sam. We create a depth map based on the images, the 16 images that we get, low resolution images. And this is a raw depth map. And then by using a number of regularization techniques, we can actually fill in all the holes and create a very accurate depth map. One of the things we do need to change is probably some of the coloring because of the distance. There's a lot of yellow there when it's really degrees of yellow. But once you get something like this, the next sort of obvious thing is, well, let me start building 3D models. Right? With one picture, we're not capturing an entire 3D model, but probably with about, I think we've done it with about four shots, I can actually render a very accurate 3D model. And one of the reasons I can do that is because I know the depth to or the distance to everything in the object. So stitching that together is really easy and not very error prone. Another application that, this came from automotive, right? This is actually the issue of, someone bending down in the passenger seat and the airbag goes off. It's actually quite dangerous because it's very close. So one of the automotive applications, for example, is sensing where all your passengers are and actually having airbags go off or on and calibrate them and so on. There's actually about 15 different applications in the automotive industry for this type of camera, because once you actually get depth, you can start to do things like collision avoidance, making sure you stay in lanes, read the car signs. You can probably do gesture and all those things. I don't know, there'll be some safety issues, but it really is a very unique way of actually using imaging and depth that you calculate to actually increase safety. Here's actually an example of a social network, sort of the normal thing you do. Take a picture. Here, Patty's taking some pictures with her friend and her bear. Decides to right there on her social network change who she's going to focus on. She wants to focus on herself, not the bear and the friends. She posts it. She gets tagged. I guess the guy in the back says he really wants to be her boyfriend and cuts the bear out, puts him there. Patty doesn't like that, so she cuts him out, brings the bear back, and off you go. Right? This is, again, all on your mobile phone. Obviously, you can still do it on your web, your PC, but the algorithms we have and the depth map we capture allow actually quite infinite flexibility when you start thinking about applications. From a Facebook or a social site, there's all kinds of advantages when you offer this kind of capability on your cell phone, right? This is not using Photoshop, which 99.9% of consumers can't manage. It's just reality. It's too complex. So in some contexts, we also think for ourselves of bringing Photoshop to your grandma, right? Where these things are infinitely easy. I talked about the ability to measure objects or distances. So, there's something about it's a piece of art there and you want to measure it. Take a picture of it on the wall and you can actually measure it. Pretty easy. There's even applications where I want to do volumetric calculation of how big is this package, right? Not I won't say that company or other companies, but some companies have approached us for exactly that problem. If I knew what the volume was by the time that the driver gets to his truck, he can be told exactly where to put it, and my central depot already knows what's the volume of every package coming in. There's actually very large scale efficiencies that they can get on something like this. And this is, again, every time we talk to someone, once you can measure distance and capture that depth, the level of applications are now no longer about taking the picture and having nice filters and doing unique things. It's now really going up level, where your photograph now is really something immersive that has a whole set of business commercial uses. More examples. Okay, I guess. So our camera is really a software camera. We are a software company. We design an ultra-thin sensor and lens in an array. And the secret sauce is in that IP that's with that, but also in our algorithms and having them implementable on a mobile device. Array cameras are not new things. They've been around for decades, but to be able to shrink it down and actually have the computation capability along with the algorithms to do it accurately with high quality imaging. That's kind of our secret sauce. And we have a set of advantages, everything from high resolution, the depth-based imagery, and I'll show a couple examples from an imaging perspective, some of the advantages that we have with this, and we'll talk quite a bit about how we're actually implementing this on Qualcomm's processors. One of the other advantages of this architecture is that on traditional camera, there's anywhere from 13 to 16 parts. With our particular design, there's only 4 components, of which actually this last piece here is really software. So so what it leads to is a simpler manufacturing process. But on top of that, the scale of this can actually increase the scale by changing or increasing the resolution, or what you want to do going forward by increasing the number of cameras, decreasing the pixel size, decreasing the F number. And there are also other permutations. It doesn't have to be 4x4. It can be 1x9. There are other things that can be done. We can take, for example, one row there and say I want to have low-cut IR filters. There's not a whole set of applications that want that. Security space and so on. Here's actually an example of the 16 cameras with the super resolution software there. Here's actually an example of some of the benefits that you see. Because we have 16 cameras taking effectively the same image, slightly offset, what we're able to do is differentiate noise. So instead of smoothing out noise, we can tell the difference between noise and texture. So what you actually end up getting is much finer detail, and you also get a better low contrast image. Right? There are some really excellent algorithms for, say, traditional cameras. We actually call them legacy cameras. However, at some point, it's very difficult to determine the difference between noise and the real texture. Here's an example at very low light. On the Pelican side, you've got much higher sharpness than on traditional 8 meg camera phone on the right, as well as color fringing when you start looking at blinds in the back. A significant difference. One of the reasons we get much better color and no color fringing is that each of those cameras is actually a single color. So it's not a traditional bare camera. And what that lets us do is separate the color quite significantly and not have color leakage from pixel to pixel. So let's talk a bit about what this means in the computation required for this. So we had this running on A974. We had it demoed on Hardware Day. And there are a number of key things that were necessary to actually implement this technology and get this to market. One key enabler is you have to have killer hardware, and that's something that the 8974 really provides us. Right? These algorithms are not trivial. The really area where it's high performance is required is really when you're trying to do 1080p video and so on. You cannot have, you can't delay anything. You basically got 30 milliseconds or 30 milliseconds to do a frame and be done with it, right? Still has its own challenges, but you have, there are many ways to deal with that. The other thing that, when we've been working with Qualcomm on the 8974, is how to take advantage of some really great compute blocks that are available on the actual SoC. We have leveraged, everything from the DSP, the CPU, and GPU, and as Mike was talking about earlier, really looking at what are each algorithm, the data flow for each algorithm, and where to implement them, both from a performance perspective, a power perspective, and even a bandwidth perspective. Right? This is an application that pushes a lot of data around very quickly, and so how do you minimize going to DDR, for example, is a really critical aspect to get the right performance. Right? We've actually implemented this as a multi-frame pipeline over multiple components in the system. And on top of that, we actually have implemented our own dynamic scheduling tile algorithm. If you take a whole frame, you typically can't keep that in L1 or L2 cache. Maybe L2, but not L1 cache. And so what we've actually implemented is a scheduler that dynamically can adaptively schedule jobs, not just on one compute element or compute type, but across the DSP, the CPU, and the GPU. This also lets us have flexibility that as Qualcomm puts out the next piece of hardware, I can easily take one of those compute loads and say, oh, great, you improved the processing power for the DSP. I can now move those almost trivially to another element. That's actually allowed us also, when we have certain elements that are idle, to take advantage of them when we're doing our processing. Then there are also some powerful compute blocks in the hardware themselves that we've been able to take advantage for acceleration, as well as even image quality, right? There are some blocks here that actually, compared to, say, a software-based algorithm, that are available on the Qualcomm chipset. If we actually look at, we really have 3 or 4 main stages in our pipeline. The first stage is what we call our normalization stage. This is actually taking the data, the calibration data you normally have with the camera that's built at manufacturing time, and actually normalizing that data to take the account that you've got 16 different cameras, and every camera is always different. In fact, every camera and every phone is always different. Right? Every sensor is actually unique. There are pixels that may not be there. There may be cluster defects. The lens will always be slightly different within some tolerance that we've worked with manufacturers. The next step we actually do is our whole image fusion and depth map generation on the CPU. Now, why did we choose the CPU versus the DSP and so on? By looking at those algorithms, the workloads, cache sizes, some of the things that we want to do, we've placed these here. We actually have experimented in different places. And a lot of it will come down to the bandwidth you need, the data pattern, in terms of your data access patterns, as well as some elements offer more flexibility than others, right, based again on the algorithm. And then we have a number of post-processing steps on the GPU, which does a great job at compositing, color, other types of things. Right? We have some very special color processing, which because we have more data effectively, we're able to, I think, do a really remarkable job in terms of the color processing. And then there's the standard hardware acceleration for H.264 or JPEG encoding. What we have seen is that, like most of these types of applications, you put all the stuff on the CPU when you first start. and then you start. And what we have been able to see is that on specific elements, we've seen a performance increase from moving from the CPU to the DSP or GPU, up to actually 100x. It's hard to believe, but it's very true. Now, that's not everything. There are certain key parts of the algorithm that work really well with the instruction set, for example, on the DSP. On the power side as well, very significant improvements. And when Mike asked me, what's the sort of the overall improvement from just a CPU-based system to something that's heterogeneous across multiple elements, somewhere in the 3 to 5 range in terms of overall performance improvement. I think the other key thing to mention is that it's not about sort of using each one of these elements as ships in the night in different verticals. So I got this particular compute, let me put it on the DSP or put it on the GPU. In our particular application, I think numbers that are coming up forward, the actual data flow is very important. So you need to actually build, you have to have hardware that will let you support sort of cooperative compute when it moves across these compute elements, both in terms of data movement as well as how you distribute that compute. And I think that's something unique on the Qualcomm chipset, and I know going forward, I think that's become more and more important as you get more data. You're going to want ways that you can move it seamlessly across multiple compute elements without having to go to DDR, for example, or even passing forward little bits of information to the next compute block. So the summary, we really look at this as a leading edge mobile platform. It's massive compute capability. We're going in the, very, very high. The architecture is quite flexible, and we found that as we move things around, and we've actually had to balance different workloads and different memory loads and so on. What has happened is that during this process, using, for example, the early prototype software and hardware that was available, much before the chip was actually available for mass production, working for Qualcomm really helped accelerate our time to market. We actually had much of this running in February this year, and the first products with the 8974, I guess they're shipping now, right? So that actually was very, very beneficial for us. The other thing that we actually found that it was not just about the chipsets, as most software developers know. It's about the software that runs on it and what you can take advantage of. So, Qualcomm, for example, has added a number of software frameworks on top of, bare Android. For example, the camera framework. And that actually has made our life, it's actually made it easy in some cases. In some cases, it's made it a little bit harder. But the key thing is there was a lot of leverage so that we don't have to implement as much, as a company in terms of all the things we need to do. So I can plug in my different, call it ISP, my software ISP, in a way that I can leverage all the overall capabilities, and those work then seamlessly with, for example, an Android OS. Tools actually, I think, have actually improved quite a bit. The latest QView, and I just saw the power management tool. I think these are things that really make a big difference when you're actually trying to build real products. This is something that certainly we have worked very closely with the Qualcomm team, both in terms of learning, both in terms of getting feedback, and they've actually made some changes very quickly as they've seen the types of workloads we're pushing through the system. And then I think, at the end of the day, when we look at a product and who we're going to work with, clearly we're going to work with leaders in mobile and that particular company. But as a startup, we have to look at the whole package. It's not just about the chip, it's about the software, it's about the support, it's about who are the OEMs that are going to deploy this. And that's something that we found very positive working with Qualcomm. And at the end of the day, for our application, it's really about being able to use every element of the compute and use it effectively. So the one piece, you know, as we walk away on this one, at least about our camera, right? You've got a digital camera, it's got a traditional set of features, and people are improving every single day. I saw some amazing things in some of the demos today on just a traditional camera. What we're really trying to do is Pelican, is we'll do all those, but there's a set of things that we can do with our particular technology that really transcend just about taking a good picture. It's really about a different set of applications and experiences that can be built with that depth-enabled camera. And here's just some press and different things that have been said about our camera as we're taking it to market with several OEMs. That's it. Thank you.